Hi, thank you very much. Yes, as mentioned, my name is Matt Commons, and I'm the lead product manager for HFSS here at ANSYS. And today's ANSYS 18 Innovations webinar will be covering topics in high-frequency electromagnetics. Now, we'll start the presentation by talking about some of the enhancements and advancements in our solutions for antenna and wireless systems. And we'll be covering a range of topics regarding performance and accuracy improvements, improvements to design workflows and antennas, some interesting enhancements for 3D component assembly, hybrid and SBR plus solving, where we combine finite elements, integral equations, and shooting and bouncing ray solutions in one environment, as well as enhancements to our RF environment, namely enhancements to our EMIT product. In detail, we'll be talking about topics like a new technology we call broadband adaptive meshing, some MPI enhancements to our frequency sweeps and overall enhancements to the speed, improvements to the antenna design kit, including the addition of some new antenna models. In detail, we'll talk about the 3D component browser, some topics regarding encrypted components, as well as the data protection. SBR solver is now integrated in the HFSS desktop. This is sort of our first step in integrating the technology from Dell Cross Technologies that came on board about 1.5 years ago. Some nice enhancements to our one-way our hybrid solving techniques, as well as our links between HFSS Savant and HFSS and EMIT. Now, real quickly, we'll do a quick sort of broad overview of the electromagnetic high-frequency solver portfolio at ANSYS. And it starts with, of course, HFSS and finite elements. So HFSS has been around for decades. It's been a staple solution for electromagnetic engineers for modeling and designing and simulating devices that range anywhere from passive components on ICs up to large antenna arrays. Now, finite elements is a great solution when you get up to tens of wavelengths and you have a high degree of geometric complexity. But at some point, it starts to run out of gas as you get to very, very large electrical size. So we also have a 3D method of moment solution that is integrated with HFSS that we call HFSS IE. And one of the interesting technologies that come with that is our PHEVE technology, finite element boundary integral. And then, of course, new to shooting and bouncing ray new to R18 in the desktop is the integration, beginning of the integration of the Dell Cross shooting and bouncing ray technology. And all of that technology is going to be pulled together and held together by our domain decomposition backplane solver, which is the sort of the heart and soul of DDM as well as our hybrid methods. Now let's talk about SBR, or shooting and bouncing ray. What is this methodology? Well, it's an asymptotic technique that's complementary to HFSS. So, for example, in a flow where you're using HFSS and SBR, or formerly known as the Savant product, you would use HFSS to model the antenna component, and then use the results from that antenna analysis to source an asymptotic technique to allow you to tackle really, really large antenna platform integration challenges in a very, very efficient and fast manner. Now, it's an extension of physical optics techniques where it's extended with multiple bounces through geometric optic ray tracing techniques. It's very powerful. You start with a source point, like an antenna mounted on the top surface of this aircraft. You shoot out these shooting and bouncing rays. They paint new currents at various scattering points on the aircraft, and those additional currents are added to the overall pattern results for the radiation pattern for the antenna. And just a little more detail and a little more advancement, our shooting and bouncing ray plus technology is an extension of the SBR technique where it adds correction factors such as physical theory of diffraction, uniform theory of diffraction, creeping wave technology, as well as curved surface divergence factors. So it's an extension of shooting and bouncing ray for a much more accurate, much more physical solution. And again, you start with bouncing rays, you paint currents. Those currents can either they themselves shoot additional rays, which will create additional painted currents. We can take into account corrections for edge current PTD effects, as well as UTD edge diffraction, and take into account creeping waves where you have sort of ground currents creeping around over surfaces that the antenna is mounted upon. That all ends up with the image in the lower right-hand corner where you have not only the original source antenna, contributing to the far field patterns, but also this large number of painted surface currents on the scattering object, allowing you to understand exactly how the antenna is going to perform on the platform. So it extends our accuracy from the antenna level all the way up to the platform level. And of course, it's very, very efficient as an asymptotic technique. And as you can imagine from a quick description of the shooting and bouncing ray approach, it's very parallelizable. So you can solve very, very large, complex problems in very, very short period of time, modest amounts of memory, and solve very, very large electrical size models. Now, in R18, what have we done? Well, we've added the first instance of a shooting and bouncing ray technique absent the extensions of the plus correction factors. So in this approach, in the same desktop that you've been used to with HFSS, you can run a combined HFSS finite element solution, such as analyzing an antenna integrated into your rear view mirror of this vehicle. And then on the vehicle, we define a shooting and bouncing ray domain where that antenna from the HFSS analysis illuminates that domain, and we use the shooting and bouncing ray technique to understand how the platform affects the overall radiation pattern. And this is so important to antenna engineers and antenna integrators, where understanding the antenna performance alone in a pristine environment isn't going to be accurate enough or correct enough to really allow you to understand how the antenna will perform when integrated into its environment. Now we're still maintaining the legacy Savant interface. That will be going on for a few more years. So there was additional enhancements in the R18 version of Savant standalone, most notably end-by-end coupling mode, which allows you to, in one simulation, simultaneously generate far-field patterns as well as S-parameter coupling terms between multiple platform-mounted antennas. Overall, the multicore scaling has been improved, including enhancements with GPU performance for rendering, for example, of imported near-field antenna sources. And some of the user defaults have been improved. We found that over the years, everybody was setting defaults a certain way to most notably guarantee higher accuracy, so we've adjusted the default. So out of the box, it has a more user-friendly behavior. Now, in this whole concept of hybrid solving, where we're using a combination of finite elements or shooting and bouncing rays I talked about earlier, or we're using finite elements and the integral equation solver, which has been around for a number of releases now, we've done this rigorous coupling scheme where we couple the finite element solution domain and the IE domain at a matrix level. We've added in R18 a new one-way option for faster extraction. So let's say you want to do an antenna mounted on an aircraft, like this example here, and you've modeled the antenna with HFSS and finite elements and using the Phoebe boundary for the outside boundary condition. You can mount that on the aircraft, and you can run a one-way extraction for a much faster extraction. This example here was almost a 2x savings in simulation time, or greater than 2x savings in simulation time between the two-way and the one-way. Why would you use this? Well, in the one-way, you can use that early in your upfront simulation efforts. Later on, you turn on the two-way fully coupled capability to get the most accurate solution. And for this particular example, you can see really only on the back side of the aircraft, the top side of the aircraft, where the results significantly affected, and even that effect was pretty far down in the signal to noise and the dynamic range. We've also enhanced our antenna design toolkit, which is a feature that's been available with HFSS for a few releases now. The antenna design toolkit is an ACT extension inside the HFSS platform that allows a user to synthesize some basic antenna topologies and models to, for example, start their antenna analysis job. We've enhanced some of the usability for the flow, made some of the flow a little bit simpler, a one-click completion step. Easier to use tree structure to browse through and pick your antenna topology of interest. We also added some new topologies like reflector antenna and Yagi-Uda antenna topologies. And probably most notably, we've added a custom antenna topology where if you have an antenna design that you've saved as a 3D component, you can now incorporate that antenna topology and that antenna design in the antenna design toolkit. So if you want to reuse one of those designs again and again, or maybe you want to share that with some of your colleagues, you can integrate it right into the antenna design toolkit. So the steps are to find your 3D component, go to the add antenna category, browse to your 3D component file, typically in your installation directory, select your antenna, and park that right there in the installation for use later on. And as mentioned, the antenna design kit, the overall support for the library is extended with 18 additional footprints from what we were working with in release 17. And this is really just to extend the coverage of all the different antenna topologies that are out there and people are interested in using and starting out their design flow with HFSS. Now our EMIT product is another product along with Savant that came from Del Cross Technologies, and we've extended our capabilities and our coupling between our desktop technologies and EMIT with a Nexsim EMIT data link. Now what this data link is, it's an automatic creation of an EMIT compatible transmit model, behavioral model from a detailed Nexsim circuit design. So you can have a detailed model of your radio system in Nexsim, laid out, simulated, results generated, and a single click gets you to an export window, which allows you to pass that radio model information directly over into EMIT. It's very quick, easy to do. You have that model, that radio model, ready to run in EMIT. In addition to the Nexsim EMIT data link enhancement, we've also extended GPU support for EMIT, which is, again, it's a highly scalable technology that can be parallelized. Some nice improvements and speedups overall with GPU technologies and enhancements and across a range of projects, 5 projects that's been tested here. Some other enhancements to EMIT in 18.0 is new radar modulation schemes are now available, including FM, non-FM, CW, a range of radar modulation schemes can now be added. In addition, you can create custom fixed coupling schemes in your in EMIT, where you, as a user, you can define in what frequency bands you want to tolerate certain levels of coupling or detect certain levels of couplings between multiple antennas operating in different bands. Now let's move on to our topic, next topic about meshing. Meshing is a very, very key part of HFSS, and oftentimes when we talk to customers they're very, very interested in hearing what we can do to enhance meshing, most notably speed. So in R18, the meshing technology has been improved in the refinement step part of the meshing scheme. And these are steps that are associated with refinement, the adaptive mesh from pass to pass, if you have any seed operations in your mesh definition, or if you're utilizing curvilinear elements. All these different parts of the mesh process have been sped up either through algorithm improvements or in some cases application of multiple cores. And a real quick example on an antenna array that's laid out in both HFSS 3D as well as 3D layout as well as HFSS 3D using our finite array DDM technology. Using compute resources of 16 cores in 3D layout, the phi mesher is 25% faster versus compared to the last release. The classic mesher in R18 is 47% faster compared to the previous release. And even in 3D, the classic mesher has been sped up overall through some of the application of these technologies by 13%. Speed is always a critical issue that we hear from our customers with respect to meshing. So we've also done some improvements for our IE solver as well as our IE regions. Most notably, the initial surface mesh generation time has been enhanced with HPC technologies. In this example of a dish antenna with a feed horn and subreflector, utilizing 16 cores compute resources, the result is 1 core meshing in R18. Overall, total time is 35% faster than the previous release. And leveraging 16 cores, we get some additional speed up, increasing the speed by 46% R18 versus R17. Now, that meshing topic brings us to what I think is one of the most impressive new technologies that our developers have implemented in HFSS for a number of releases now, and this is broadband adaptive meshing. Now, broadband adaptive meshing, first let's talk about adaptive meshing in general. So that's the cornerstone technology of HFSS, and it's what makes HFSS so powerful and so valuable to our customers, because we let the physics, the geometry define the mesh. We don't ask the user to define the mesh and determine how to get the right answer. We let the physics guide it. In this animation here, we're looking at an antenna model where we're looking at the mesh being adapted from pass to pass. And in the lower plot, we're looking at the change in the S-parameter response as a function of this adaptive meshing. And this is really the heart and soul, the power of HFSS. The ability to automatically adapt for an accurate mesh that's efficient as well as reliable. This is why people rely on HFSS for accurate solutions. It adds mesh elements in areas where dense mesh is needed to accurately compute the EM fields. And as mentioned, it's a key technology that ensures the automatic accurate electromagnetic simulation. And we've been using it from day one in HFSS. And we're using a single frequency approach to adaptive meshing. You start with an initial mesh, you solve the fields at that solution frequency, you check the performance of the device at that point in time, you capture S parameters or maybe some far field quantities, you do a mesh refinement, solve it again at that frequency, and you check how those parameters have changed from pass to pass, and you set a convergence criteria where you say, okay, I've done my adaptive mesh, is it converged, now move on to this frequency sweep. For broadband accuracy, though, the choice of the mesh frequency can really impact the accuracy of the results. You can mesh at a single frequency representing a typical responsive device, and many of our customers have used that technology for years for accurate solutions, but not always reliable. In some designs, and I'll show you an example in a few minutes, you really do need to mesh at multiple frequencies. And we've had multi-mesh capability for many years, decades even, where you can basically mesh at one frequency and pass that mesh to another frequency and do adaptive meshing from there. But that approach could be computationally expensive. And then the question was always coming up, so where should I set my meshing frequency? And it could depend on the application, whether you're doing antennas or you're doing an IC package extraction, but it's a very common question from our customers. Should I use the midpoint of the frequency band? Should we use the highest frequency of the frequency band? What about square root 2/2 of the highest frequency? I actually know customers actually use this rule. But hey, what about if we could use all of the above? And that's what broadband adaptive meshing is going to bring to the table in HFSS R18. In broadband adaptive meshing, we're going to still start out with that same concept, but we're going to take that initial mesh and we're going to solve it at multiple frequencies and use information from all those frequencies to adapt that one mesh, and then do that similar refinement process where we go back and we keep track of, at all these different frequencies, we can keep track of S parameters or far field quantities or field quantities, just as we've done with a single frequency, but we're using information across the entire frequency band to adapt the mesh. And what's really powerful about that is it really removes a lot of the uncertainty about what frequency should I use for my adaptive mesh. You can now use all the many frequencies across the band that you're interested in. So multiple points can get solved. They can be solved in parallel by leveraging HPC and multiple cores or multiple compute nodes. An interesting little feature of this approach is if you solve multiple frequencies in parallel, they can precede your frequency sweep. So you get a little bit of a kickstart to your frequency sweep analysis. So overall, we see faster frequency sweeps using this broadband adaptive meshing. But the real key to broadband adaptive meshing is removing that uncertainty question about where should I set my adaptive mesh. Set it across your frequency band, take advantage of HPC hardware, and really remove that uncertainty of where you should do adaptive meshing. So a real classic example of device where people would do multi-frequency point meshing in the past is a diplexer like this model here, this cavity diplexer here, where you have two distinct bands, a high band and a low band. Now you could do single frequency mesh in either band, but you see you get mesh concentration in one particular geometric region of the device. So neither one of these meshes covers the device's entire behavior across the response. Relies on the user to choose the right solution frequency, definitely for diplexer design, and for filter designs, typically users will do multi-frequency adapt, where they'll mesh at one frequency and pass it to another frequency to do additional meshing. But the important thing is your field behavior is very dependent on the frequency. So having a mesh that's generated from multiple frequencies is key. So here's the end result when you apply broadband adaptive meshing to that same device. You can see the single frequency meshes in the left-hand side of the slide here, very concentrated in very particular regions of the device. And the broadband adaptive mesh, where we're doing meshing in parallel at multiple frequencies, shows a more uniform, more electromagnetically appropriate mesh for this diplexer. And again, with HPC, you can perform these adaptive mesh routines in parallel at multiple frequencies. The automatic adaptive meshing process extends the capability of the time-tested single-frequency adaptive meshing process in R18. And real quickly, this is a very nice animation that one of my colleagues put together to demonstrate this, Arian Sligar. where he's showing an animation of those fields, comparing it to single frequency versus broadband adaptive meshing. And you see indeed for the single frequency point mesh, you get mesh adapted in one region of the device. For that broadband adaptive mesh, it's adapted across the entire region of the device. And the results are critical to how the meshing is performed, not surprisingly. The bold lines are the solid lines are the broadband adaptive mesh, and you can see in this example you get an accurate solution to the low frequency band, whereas the dashed line was the single frequency adapt in the high frequency band of the device. Although you get the right response of the device in the low frequency, it just isn't in the right frequency band of the device. So upper band correctly agrees with broadband mesh because solution frequency is chosen in that band. Lower band is not correct behavior, but not correct frequency band. Single frequency only generating mesh for out-of-band fields. And accurate results possible with a single frequency, but we'd have to use that linked mesh technology that we mentioned earlier. But now that's gone. In R18, we can mesh them both in parallel. So the setup in HFSS is going to look pretty similar to what you're familiar with today. We've left the single frequency approach behind. No one is going to make you do this. If you want to keep doing single frequency, you go right ahead. But there's a couple of new options in R18. There's a broadband definition where, as the user, you just define the low and high frequency of interest in your analysis, and HFSS will automatically pick appropriate frequencies for doing the adaptive mesh. Which frequencies it picks will depend on a couple of things. It'll depend on how broad the band is, whether it goes from DC to high frequency. It'll depend on how many machines you make available or cores you make available to the analysis. If you make more cores available to the analysis and there's enough memory available, more frequency points will be solved in parallel. And I have an example later on to show you that. But it's using essentially a selection criteria that's analogous to our interpolating sweep scheme for generating broadband S-parameter results. But broadband is really the approach where, as the user, we're not going to ask you to think about where to set the meshing frequency. We're going to determine automatically for you. But if you're an expert user and you want to have that control, that's available to you as well with our multi-frequency setup, whereas an expert user, you can select any number of frequencies where you want to do your adaptive mesh. You can have unique convergence criteria for multiple frequencies. You can set very, very specific frequencies. Again, you sort of have the best of both worlds. The approach where HFSS automatically determines the correct frequency, and the approach where, as a user, you can set them manually by yourself. So in an area of solver improvements, which again, like meshing, is always being asked by our users, how can we solve faster? A number of nice new technologies have been added in R18, and the most significant one you're going to see, especially if you're doing using interpolating sweeps in your design flow, is an S-parameter only matrix solve. And this is really kind of an interesting approach to solving a frequency sweep. When you're doing an interpolating sweep in HFSS, you have your mesh that you've created with the adaptive mesh process. And during that process, the fields get saved, and that's an important part of the adaptive meshing routine because those field quantities give you the information that directs you in how you're going to adapt the mesh. But once you get to the frequency sweep, especially with an interpolating sweep where you no longer need the fields, there's no need to spend any effort to extract that information. So with this S-parameter only approach, what's being done is essentially what's only being held in memory is the part of the matrix solution that's needed for extracting just the S parameters. Overall, that results in a faster extraction, a modestly faster extraction of 10 to 20%, depending on the size of the model for each frequency point. But most importantly, there's a much lower memory requirement to this approach. What does that mean with the lower memory requirement? What that means is that you can, when you're doing an HPC solve and you're solving frequency points in parallel, more frequency points can be packed into a given amount of memory, which gives us better scalability overall for the frequency sweeps. And for this example here, just real quickly to show you the difference in memory for a fairly modestly sized project, about 2 gigabytes, you get almost a 2x savings in memory overall. But as the projects get bigger and bigger, your savings gets better and better in terms of memory when you go to this approach. Now, one thing to point out, this is not an approximate solution. We're not changing how we're solving for the S parameters. We're changing about how we're dealing with the memory. You can look at the solutions down to any significant digit you want to. You will not see any difference in S-parameter results, as we're demonstrating here with an overlay plot where we solved it with and without this S-parameter only approach. There's no user setting for this. HFSS is aware when it can and cannot use this, and just automatically will take the savings with this approach. And just to give you an example of some of the memory savings you can realize, especially as the problem sizes get bigger and bigger, we have a few examples here. We have a connector on a couple of connectors on a printed circuit board design, a more complex layout of a cell phone, and an even more complex layout of a cell phone where you have all the detailed housing around the cell phone device. You can see some very, very significant memory savings as the problem size grows, even to the most extreme, over 6x savings in memory for a very, very large simulation. What does that mean? Well, whereas before you may have only been able to solve one frequency point in parallel and you're given a block of memory, with that savings in memory, now 8 can be solved in parallel. Obviously fewer cores per point, but we get better scalability when we solve frequency points in parallel, so we get better speed up overall for the frequency sweeps. And in this example, we saw almost a 2x speed up in the frequency sweep extraction. Other improvements to the solver technology in HFSS, and when you look at the profile of HFSS, there's all these different steps, and for years we've really focused on the solver line where we're actually extracting the matrix, but other parts of the solution process can begin to dominate as we see users really starting to do some very, very complex designs in HFSS. One of those processes was matrix assembly, and that's been sped up through a combination of algorithmic improvements as well as implementation of HPC in multiple cores. And for this, fairly small example, we saw 74% speed up overall for the solution time. But matrix assembly was beginning to become a fairly significant part of the solution time. And in some very, very extreme examples that we've seen from some of our signal integrity customers, where they're modeling very large packages with hundreds or multiple hundreds of ports, this part of the solution process could actually begin to dominate overall, and it's been sped up significantly for those large models in release 18. So let's put this all together with a little bit more complex model. It's a model we've been working with over the last few releases when we wanted to demonstrate how things are solving faster in HFSS. It's a package on PCB model. Here we're analyzing 2 differential pairs, so 8 terminals overall. We're going to do a frequency sweep from DC to 20 gigahertz. Hardware we're using is a 14-core Intel Xeon processors, 2 gigahertz, 2 processors per node, 2 nodes overall, so a total of 56 cores for this particular analysis. And we're taking advantage of our auto HPC technology, which, as a user, you just say, here are the cores you can solve on, and we'll automatically figure out how to take the best advantage of them. So real quickly, how do the results compare when I do 2016 versus 2017, or R17 versus R18? Very comparable results, almost spot on, very, very difficult to see any differences. What about solution time? Let's see. Okay, elapsed time in 16 is 224 versus 149, so it's an hour 49 in 2017. This is the frequency sweep, so the previous times were the meshing times, the adaptive meshing times. You see the frequency sweeps here have been improved considerably, and this is really a big payoff from the S-parameter only solution, where the memory has gone down. We can pack more frequency points in parallel. We see a huge speed up overall, greater than a factor of 2 speed up for the frequency sweep. So looking at these in more detail, in our previous release, release 17, total simulation time was 11 hours. Release 18, total simulation time is just under 6 hours, or almost 89% faster overall. But look at that speed up for the frequency sweep, 114% faster in release 18. That's a big payoff for that S-parameter only matrix solve. Now, let's add in one more variable that's been introduced in R18. What about broadband adaptive meshing? Now let's add that in. So the previous example, we were just doing the quote-unquote traditional single frequency point adapt and doing the frequency sweep. Now we're going to run that same model in R18. We're going to do the broadband mesh from DC to 20 gigahertz. And what do we do here? We use auto HPC again. We say here are 56 cores. And we had quite a bit of memory on the machines, hundreds of gigabytes. And so with all the memory available, the analysis is actually able to solve 28 frequency points in parallel during the adaptive mesh routine. So adapting all 28 points in parallel, adaptive mesh took a little bit longer than the single frequency adapt, kind of to be expected, right, because we're using fewer cores per frequency point. not too bad, but a really nice payoff in frequency sweep time, and much of this comes from two factors. Number one, we preceded the frequency sweep with 28 points after the adaptive MASH, but also, and very interestingly, the adaptive mesh for this analysis was actually smaller, even though it had the exact same convergence criteria as a single frequency adapt. This has been kind of an interesting artifact that we've seen with broadband adaptive meshing, where it can actually take fewer adaptive passes and an overall smaller mesh to get a converged answer across the entire frequency band. Again, results are very comparable, slightly different, not surprisingly. We're doing meshing at multiple frequencies. In fact, if they were exactly alike, I'd be really surprised. And you can see some differences at the higher frequencies, but overall, very similar response to our traditional approach. And the payoff between 18 and broadband adaptive meshing in 18, a little bit slower on the adaptive mesh, but the sweep is faster, total time's faster. But look at the payoff between release 17 and release 18 with broadband adaptive meshing. An overall speed up of 124% for this model. So I think the combination of broadband adaptive meshing that gives very reliable, very secure answers, doesn't require the user to think about exactly where to do the adaptive meshing, as well as enhancements to solver technologies like S-parameter only matrix solve and speed ups with matrix assembly, you're going to see some very, very significant speed ups in your solution time in release 18 for HFSS. Now, we've also enhanced the HFSS transient solver. It's a finite element based time domain solver that can be added on to a seat of HFSS. The implicit solver technology has been sped up. We've improved the auto HPC performance for both transient solver technologies, and we've added PMLs and shell elements for both solvers. So now the transient solver has very, very common features and capabilities with our frequency domain solver. Anything you're familiar with frequency domain, you can do on our time domain solver. Where do we see users extracting with our time domain solution? When they want to look at time domain answers, like these fields propagating in time, or if you wanted to look at, for example, TDR in a device. With the time domain solver in HFSS, which uses the same meshing technology as HFSS frequency domain, you can extract the time domain information along with the frequency domain information that you do with HFSS. Now, also in R18, we've made a big addition to the base product of HFSS. And to talk about this addition, I'm going to go back in time just a little bit, a few years, back to HFSS 12.1. And this is probably around 2010, I'm guessing, maybe 2011, where we introduced our new IE solver. And what was IE? Well, it stood for integral equation. It was a 3D method of moment solver technology that you could add on to an HFSS seat. A very, very efficient solution for large open radiating problems like antenna on platform or RCS analysis. Just like HFSS, it was adaptive meshing was built into the technique to ensure accuracy. We have multiple fast solver technologies, both ACA and MLFMM. Easy to use interface, because if you knew HFSS, you know this interface. It's all there, same interface. It could even utilize results from HFSS to be a source in a coupled model approach. And where was it what was it addressing? Electrically large problems, which nowadays this isn't so large, but back then this was a big problem. We were analyzing a VHF antenna on a UAV drone, almost 20 lambdas in size. Using IE, you could solve a very reasonable period of time with a very reasonable amount of memory. Again, adaptive meshing was built into that and is built into that technology. This is an interesting analysis of that blade antenna, where we're looking at the response from both the finite element solver of HFSS and the IE solver converging to the same answer using adaptive meshing. So again, we're using all that great technology that you're familiar with over the years and applying it to 3D method of moments. Another big one that came in this release was FEBE, finite element boundary integral, where you could truncate your finite element solution with an integral equation version. Hyper accurate solution to the free space radiation condition. Utilize the surface only mesh on the outside surface of the ABC to solve for the equivalent surfaces for the free space radiation condition. You combine finite elements, the ability to handle complex material and geometry, and integral equation or method of moments for large open problems. And you have this terrific technique, FEBE, where you can use a hyperconformal error volume to shrink your finite element solution and still have a very, very accurate problem to the far field pattern. So it was using the best of both worlds in finite elements and boundary integral. This technique was then extended in HFSS 13 with a more general hybrid technology. We're using finite element in IE, but instead of being restricted to the Phoebe boundary, you could also add a 3D method of moments object in that same domain with finite elements and solve a fully accurate, fully coupled matrix solution automatically in one desktop at HFSS 13. And now in our R18 of HFSS, IE is now included. So if you have R18, you now have available to you the HFSS IE solver. So Phoebe now included in HFSS. Hybrid finite element IE solver is now included in HFSS. So what we're doing here with HFSS and R18 is in one product you have both full wave finite element and method of moment solutions in one product. And it really extends and delivers a single solution for a complete antenna synthesis design and integration platform at R18. So remember, we talked about the antenna design kit earlier. You start with that kit to synthesize your antenna, solve it with finite elements, and do a platform integration analysis with IE, all in one platform, HFSS. So moving on to more of a usability area topic, let's talk about some of the improvements to our 3D modeler. I actually, as a long time user of HFSS, I actually find these improvements some of, there's no other word for it, some of my favorite. I love these little usability things. And the first one is a really nice feature that I've been leveraging quite a bit. It's tree grouping and hierarchy in the model tree. Now in the model tree, if you've got a bunch of parts, instead of flattened out and organized according to materials, you can add a hierarchical levels or a set of hierarchical levels actually to organize your designs. And this is really just an organization thing. It has nothing to do with the actual geometry and how you create it or anything like that. You can do everything you're doing today, no change to your flow, but this hierarchy, this tree grouping allows you to package parts of your design into very specific categories in your tree. It just helps you organize your design flow overall. It's a really nice enhancement. I use it all the time. You can have multiple levels to the hierarchy. You can have all sorts, any range of objects included in this hierarchical group, including 3D components, UDMs can all be in the history tree. You can have unlimited nesting. You can do group actions on these hierarchies like copy, paste, or delete. You can move objects from group to group freely. It's very flexible. It's a really great way to organize your design and sort of create some sanity over what we see people doing today with some very complex and difficult designs. It supports CAD assembly on import, which have assembly definitions in them, so that assembly can be captured and saved, which is very nice for the supported formats like Pro-E and SolidWorks. On the 3D component improvement area, now 3D components is a technology we've been rolling out over the last few releases, which is a way for you to capture parts of your design and reuse it, as well as if you want to, you can encrypt 3D components to share your design with other users, but not expose your design to them. There's a new component browser window where you can organize your 3D components on the right-hand side of the window, just to categorize them. For example, we have a number of antenna topologies now included with release. You can have your own personal library of 3D components. So very easy access to 3D component definitions. There's a drag and drop feature, which I'll show you in a second in the video, which is really nice. And 3D components and this browser window really makes it easy for you to manage your favorites and easily access them during your design flow. A new feature with respect to encrypted components, if you're sharing encrypted component with password protections, there's now an edit password that you can add to the component definition. It's a unique secondary password that you can give to an end user to do their own editing of the encrypted component if you wanted to. So overall, the power and the value of 3D components is it really provides a powerful collaboration workflow. With this drag and drop capability, with the ability to encrypt these components, allowing you to share them across the supply chain, really allows our users to collaborate with one another and really create powerful, efficient, effective, and accurate systems. So here's a quick video of 3D components and the library browser, the drag and drop. So I have I'm creating a pi filter on a print circuit board assembly. On the right-hand side, we have the browser window. I drag and drop in an inductor model that I've created. I can play around with some of the parameters that I've defined for this inductor model. In this case, I can play around with the width of the inductor. I can go to a new coordinate system location, drag and drop in a capacitor definition, and then a third location to drag and drop in another capacitor definition. What's nice about this is a way you can reuse your designs. You can share these 3D component models with colleagues and vendors or customers. Let them use these components in their own design flow and very easily integrate them into their design. So that's a really nice feature. This is one of my favorite features, along with the hierarchy in the 3D modeler of HFSS R18. Another interesting feature can help people who are dealing with more complex designs where they want to quickly remove some of the detailed features that aren't so important to the electromagnetics. There's a new model simplification feature in the Electronics Desktop 3D Modeler. Allows the user to really quickly grab parts of a design and remove fillets and chamfers or screw holes very, very quickly with one simple modeler step. This is a real savings in time to set up designs, particular designs that you've imported from external CAD sources. There's been some nice improvements to the 3D far field patterns. This is the little stuff that I think release to release really makes your job easier, especially when you want to demonstrate the results of your simulation. A modernization of the 3D polar plots, so we've added grid and axis scaling, improved some of the lighting in the modeler, just a little more improved visual effects overall. Another favorite of mine in this release is an overlay. We've had overlay of far field patterns in the 3D modeler for a number of releases now. Now we've made it really, really easy to get to. If you have a 3D polar plot definition or 2D radiation pattern definition in your HFSS design, a simple right-click on the polar plot definition, and you go down to overlay visibility, and that quickly overlays the visibility of either a 3D polar plot or a 2D radiation pattern plot. That really helps you when you want to understand exactly how your radiation pattern is oriented with respect to your device, and of course, if you want to create a presentation to demonstrate how your device is working. In HFSS 3D Layout, which is our alternative workflow, which comes with HFSS 3D, the layout-based workflow in HFSS, there's been some significant improvements over the last few releases to address an application that we have a number of customers that ask about it, which is to run simulations that combine designs that are drawn in layout, such as a tool like Mentor or Cadence, along with a 3D model. For example, this example here, where we have a combined solution of a complex printed circuit board with a 3D connector model. Now, this was introduced in the last release, release 17. It gave you a way to link a 3D model of a component into a 3D layout model of a printed circuit board and bring those components in, orient them on the device, and do a full simulation. Now in release 17, the way this full simulation would work is the PCB would be solved standalone. The two connectors would be solved standalone. They would have their S parameter responses automatically connected together correctly based on how they were defined and located on the pins and layout, and you could get a full system solution to this a more complex structure combination of connector and printed circuit board. As soon as we delivered this feature, the automatic request was, hey, we need a full 3D mesh of that design because we don't want to take the approximation of cascading S parameters at the interface between the connector and PCB. We want a full 3D mesh, and that is available today. Now in 3D layout, you can bring in a connector design, locate it on the board, and you can generate now a full three-dimensional mesh of that design and run it and solve it fully coupled, taking into account all electromagnetic effects. In addition, some interesting system enhancements to 3D layout. As I mentioned, you can assemble ECAD and MCAD models together, like this example here with a DIM card and a connector on a PCB. There's a new solver technology that's available in the desktop. You have to have the SI-Wave product to run it, but you can now run an SI-Wave simulation on a layout design in HFSS 3D Layout. So SI-Wave is our fast PCB extraction solver, and you can see it's a sort of a natural addition to the HFSS layout flow. So you can also connect up to this design in 3D Layout other information like the transmit and receive devices. You can have a schematic connection look at IBIS and IBIS AMI modeling, QuickEye and Verify extraction. You can do both HSPICE simulation, although that does require the Synopsys HSPICE license to run HSPICE simulation. And you can now do PSPICE models in HFSS 3D layout using the Nexum solver technology with the PSPICE syntax. So all this is available in a combination of our circuit simulation and HFSS 3D layout. Desktop and documentation, some nice improvements there. This one is really an interesting enhancement, and it's a resource optimization based on where you are in a simulation, really associated with frequency sweep jobs. Now, if you really think about how an HFSS simulation is broken up, it's really broken up into 3 steps. There's the initial mesh generation, there's the adaptive mesh generation, and then there's a frequency sweep. And really, when you look closely at these, all the different parts of the HFSS solution process, they all sort of need their own unique amount of resource hardware. For example, the starting mesh, all you need is the hardware on a single machine. Now with this 3-step option, you can define a unique set of HPC resources for that part of the simulation process. Now, when you move to adaptive meshing, you can add more machines, more core to that part of the solution process, and apply the HP resources then. And this is all automatically handled in the scheduler, integrated schedulers in the electronic desktop. So the key here is you're not unnecessarily reserving and holding resources for the adaptive mesh, or more so the frequency sweep, when you're, for example, creating that starting mesh. So you can define a unique set, a unique size. You can size your HPC resources appropriately for the different part of the HPC, of the HFSS solution process. Really nice way to really optimize how you leverage your HPC hardware. We've added job monitoring and abort in our scheduler platform. We now support out of the box the ANSYS versus the legacy ANSOFT RSM cluster integration scheduler. We're still supporting the older ANSOFT RSM, but we now support out of the box ANSYS RSM, which also includes MPI distributed solves in release 18. And also, this is a bit of a common request we've had from a number of our customers, especially ones who use Windows HPC. You can now define a non-exclusive support, which allows you to run multiple jobs on the same machine. If your jobs are small and you don't want one small job consuming all the resources on one machine, you can let multiple jobs run on that machine. So enhancements to desktop is we have direct integration of the ANSYS Design Explorer tool right in desktop. Design Explorer is a tool, or DX is a tool, which allows you to do design of experiment analysis, extract information like a response surface of your device with respect to a variety of parameters, such as an etching or a bottom layer thickness on a PCB. We've improved our EKM web portal. It allows you now to look at results and plots from an EKM submitted HFSS job. That's been a common request from users leveraging EKM, as well as an ability to look at to do searching quickly search through your projects and simulations, even look at some statistics of your simulations. The help has been enhanced considerably. We've extended it to a browser-based help system, improved some of the search filters. You can search across multiple products now. We've still kept the same F1 context-sensitive help, but it now brings up the browser interface. And nice feature of this is it'll now be a foundation to deliver videos and tutorials and white papers in real time to our customers, as well as updates. Just be aware we also still include a PDF of our help if you don't want to use browser-based help with HFSS. So quick summary before we go to our Q&A session. Looks like we got time for that. So in ANSYS HFSS 18. We've extended our capabilities with the addition of the shooting and bouncing ray solver to the desktop that really allows you to solve some very, very large-scale electromagnetic simulations very efficiently. Accurate, I think broadband adaptive meshing is one of the best new features to come into HFSS, probably since domain decomposition method in version 12. I think this is really going to really help a lot of our users really take advantage of the power of HFSS. Speed, our S-parameter only frequency sweeps. I think everybody who's using interpolating sweeps is going to see a nice speed up overall in the extraction of frequency sweeps. This is going to be a big hit. There's no question in my mind. Improved our usability overall with that grouping or the tree hierarchy capability in the modeler, as well as the 3D component drag and drop. And probably, and as well as the collaborative capability of 3D components, where you can now share encrypted designs, where you can hide aspects of your design to end users, but they're still solving the fully complex part in their target design. Really allows you to collaborate across your design chain. And probably most notably, I think, is that the addition of the HFSS IE solver now included with HFSS. And just a couple things on this point before we wrap it up. This is only included in R18. Previous releases will not have HFSS IE in them. You have to be using R18 to take advantage of the new IE solver that comes with HFSS.